Okay, so PowerPoint slides 3. Unit systems, conversions, and sig figs. So in these slides, we'll look at kind of three main parts: unit systems, unit factor method for converting between units, and then sig figs and the rules for significant figures. So of course, if we're looking at the problem solving cycle, we are in the determine appropriate data phase. It's kind of where this presentation is going to reside. So everything we deal with in this slide deals with the data we determine, right, for our problem solutions. And so starting with unit systems, we need to talk about what they are and kind of how we use them and the different types, because we need to understand how they relate to the data we use. So first, a unit is just a determined quantity that we've adopted as a standard. And the National Institute of Standards and Technology, NIST, is a government agency that defines, controls, right, the physical quantities, the gold standards of what is a pound, what is a meter. Okay, and this is very important, especially in commerce, right? $2 a pound, right? Well, if I'm selling something that I've actually said that my pound is less, right, lighter than your pound, we have a problem. Okay, and that was a big issue a long time ago in history, where merchants would carry around their own weights and scales, right? And of course, there was a lot of debate as to what was a pound, what was a meter, and so society needed to standardize these units and how much an actual inch is, right, or a mile. So the National Institute of Standards and Technology does that in America. So physical quantities, things we can measure, right, and use in mathematical equations, examples being length, weight, volume, time, those things, right? The magnitude of physical quantities can be understood only when we compare them with predetermined reference amounts or units, okay? So we have no idea what a pound is unless we know what a pound is, right? I mean, that seems really stupid to say it that way, but unless we've already decided on what a pound is, we don't know how much we weigh compared to the unit of a pound, right? So we use units as comparisons, right? So we can talk about quantities and we all know and kind of have an understanding of what and how much we're talking about. Example being how much water flows over Niagara Falls in a second, right? If I told you that 426.6 million pints flow over a second, that may be a quantity in a unit, at least a unit that we can all at least get our minds around. We can visualize a nice cold pint of something sudsy, right, in our hand. Whether we can visualize 426.6 million of those in a second, maybe not, but at least we've broken it down into a unit that we understand, that we have, a reference point of, okay? And of course, written out without the decimal form, it looks like that. So this pint is just a unit, right, that we've agreed upon, that probably most of us know, right, or have experienced, okay? So we can visualize that, we can relate to that. Quantities in units, right? Things in red being the quantities, green being the units, right? And so we've dealt with these probably for a while now, right? You go and you spec something out and it says how many feet, how many millimeters, how many BTU, horsepower, those things, right? So we deal with units and quantities in all parts of our life, but we need to kind of understand kind of where they come from and why we do that. Of course, we have English unit system. A lot of times in America and England, that's what we use. Not always, but the rest of the world use metric. And the story that I've heard is that when America tried to go to the metric system in the 70s, the sheer cost of having to replace all the road signs from miles to meters and kilometers was so exorbitant that it was too expensive to make that change from the English system to the metric system in America, just because of the sheer quantity of re-signage that we'd have to buy and install. It's an interesting tidbit. But we deal with having to convert between English and standard now. Another system is the SI, or the International System of Units. This comes from a French version or naming of unit systems, and This is used all across science and technology, and it kind of can be boiled down to 7 fundamental units or quantities. So there's 7 base units, and everything else is built on top of these 7. So then we have a whole bunch of derived units that we basically use mathematical equations to build on top of the 7 fundamental quantities or base units. And if we look at, in this slide, the 7 base units, we have length, mass, time, electric current, thermodynamic temperature, amount of a substance, and luminosity, or luminous intensity, right? So these are the 7 units, base units, that every other unit that we deal with and we've come to deal with in science and technology and engineering are somehow based on these 7. So we look at some derived units like square meters, just a meter times a meter, cubic meters, a meter times a meter times a meter, mass, density, right? Kilograms divided by square or cubic meters, right? So we see that all these are here are just mathematical combinations of some or more than 2 of the base units. And so we can start combining these base units to form derived units, right? Some other unique naming terminologies in the SI system are frequency or hertz, force, newtons, energy, work, quantity, heat, joules, right? So these are some common types of units that we use in the SI, and some of these may be new to you, some of these may be familiar to you, but we're going to come across these a lot. Turning to scientific notation, right? We've dealt with this most likely in high school. Basically just a mechanism of saying we're going to take really large numbers like 150,000 and express it more simply 1.5 times 10 to the 5th. Okay? And the basic structure of scientific notation is either 1 to 9 digits to the left of the decimal. Okay? So we try and simplify this down as far as we can, but there's either a 1 or a 9, anywhere between number of digits to the left of the decimal. This is a more convenient way to express very large numbers. We can look at engineering notation, which is very similar to scientific, except that only 1 to 3 digits. Okay? Now what that does for us when we only show 1 to 3 digits to the left of the decimal place, it hems us in or keeps us in multiples of 3 for the power of 10. So example being 150,000 meters would be 150 times 10 to the 3rd. Okay, so 1, 2, 3, we can in our minds put a little decimal point right to the right of that 0, and that is now in engineering notation. Just another way of showing it, but it's in multiples of 3 for the exponent. Of course, 0.00021 amps could be expressed 210 times 10 to the negative 6. Of course, that's 1, 2, 3, 4, 5, and then 6, adding another 0 there, right, where we get that negative 6. So this is the engineering notation way of showing really large or really small numbers. This is even more common probably to what we'll deal with in science or in technology, engineering technology scenarios. If we look at now even another simplification of how we show numbers, we can take these times 10 to the 2nd or times 10 to the 3rd, and we can even simplify even more by just saying kilo or just K, or giga or just capital G, right? So example being, say we have the number 23 km. Okay, of course 23 km is just 23 times 10 to the 3rd. K is times 10 to the 3rd, right? And so that's 23,000, right? So we could just write 23 km instead of 23,000 m, right? Similarly, 3 centimeters we can write instead of 0.03 meters. One that's very common to us that we might not even think about is gigabytes, right? You have that little small flash drive. It's got that little text on the back of it. 16 GB or 32 GB. And then of course that simplifies us from having to write 9 zeros after that 16, right? And so these engineering prefixes or metric prefixes allow us to simplify down even more to just a letter or two that take the place of a whole bunch of zeros, either leading zeros or trailing zeros. So again, another way to show units and to show our numbers, okay? There's a whole bunch of rules to kind of how we write units. We don't put decimal points after the units, okay? We don't capitalize, okay, so we don't capitalize. We don't put apostrophe S's or S's. We don't hug them right against the number. We put a little space in there. We don't put spaces in between, okay? We leave them right up against each other. And of course, units, we lowercase letters. We don't do capital letters. And then finally, we don't hyphenate, and we don't combine units. So micro, milli, if you remember a couple slides back, those are two prefixes, right? And we don't combine prefixes because it just doesn't make sense, right? We would modify the actual number to show one metric prefix at a time. Of course, that's liters, just milliliters. So the liters is the unit, the M is the prefix. And of course, we only show one unit at a time. We don't show liters and then milliliters. It's like we don't show dollars and cents. Well, we do, but in this scenario, we wouldn't show the two, right? And then, of course, if our preference, we use a decimal version and not a fractional version of a number. So, unit system wrap up. Understand your units, understand how they relate to each other. That's going to help us understand the data that we're using, okay? Understand how to read and write them, okay? And then also, it's helpful to understand how to use your calculator, how to use Excel. We'll talk about that. We'll talk about some unit conversion and things in Excel, but for right now, we'll talk about a paper and pencil version of it. So the next little section we're going to get into is unit conversion. Okay, so the factor method, the unit factor method we're going to talk about. And this is used because oftentimes we need to convert between one unit to another. And a big time, or most common time, is English to metric. Okay, a lot of situations I've dealt with is I get dimensions from a product in metric units from Germany, and I need to convert them to English units because we're going to design and build the product in America, right? So I need to know how to convert between different units. And so we're going to talk about a couple different ways of doing that, and these are just some other examples. But how could we do that? In my mind, there's two different ways that I think a lot of students would choose to convert. I think the primarily, would be to just hop on Google or hop on a phone and just get a unit conversion calculator. The only downside to this, okay, say you're in the middle of a cornfield, no cell phone, or you're in a mine, Kentucky or Pennsylvania, right? There are places where you don't have cell phone coverage and you don't have internet connection. So the other option, which we're going to deal with and we're going to actually use in this class, and it's the only way to get credit for your activities, is a 4-step unit factor method. Okay, so this is a paper and pencil method. And so the first step is to first identify the units we know. Okay, so what units do we know? Then we look at what units don't we know. What's the solution units need to be, right? What are we trying to get to? We need to determine what type of conversion factors we need to use. And we can look at this from a table, a unit conversion table, and this is on Blackboard, and we'll show you this in class. But we need to get a unit conversion or conversion factor or two. And then we just need to set up an equation. Okay, so we need to set an equation up to appropriately show how to, to appropriately calculate our unit conversion. This unit 4 is the most important part, or the part that has the most moving parts or maybe the most complicated. And so it's really important that we set this equation up properly. So let's give an example here. We're converting 5 miles to kilometers. And of course we know we have miles, but we don't know how many kilometers we have. So our unknown is the kilometers. Okay, I mean we know we need kilometers, but we don't know how many. So that's the unknown. And then we need to determine the conversion factor. So if we looked at a unit conversion, we would see that 1 mile equals 1.6094 kilometers. Okay, and so either when we're gonna get practice in putting these in factor orientation. I'm sorry, fractional orientation. And so we either have kilometers over miles or miles over kilometers, and we'll get to how we determine that in a minute here. But that's our unit conversion. And then we build our equation. So we say we have 5 miles, okay, convert times the conversion factor equals our answer in kilometers, right? So this is just a simplified version of the equation. We have to fill in some of this unknown stuff here. We have our conversion factor being, and we chose kilometers over miles, equals, and then we'll end up having punch in the calculator and get the answer in kilometers. The reason that we put in kilometers over miles is because we want to cancel units out. So if we put it in a fractional form, and we can think of this as actually 5 miles over 1, right? These cancel out, right? Numerator, denominator, if it's in both, we can cancel out. And we're left with kilometers, okay, which is why over here we're left with kilometers. Okay, so this is how we get rid of miles and convert to kilometers. It's very important though that we set this denominator, numerator units up properly to be able to cancel out. So of course we can cancel out and we get 8.047 kilometers. And so a simple version, right? We can get another version here, a little more complex. We know we have miles and gallons. Okay, so we have 29 miles a gallon. We're going to look at getting kilometers a liter, right? We just don't know how many. If we look at a conversion, we have miles to kilometers and then gallons to liters. And we can have options of setting those up, and of course we'll put these in fractional form based on how we want to cancel out. So putting it into our equation, we see that we want to cancel miles out, so we put miles on the bottom. We want to cancel gallons out, so we put gallons on the top, and we're left with kilometers and liters, which is what we have in our answer here. Of course, all these other things just multiply across. So 29 times 1.6094 times 1. And of course, that's 1 in essence down there. 1 times 1 times 3.785. And so the numerator divided by the denominator. And we have 12.330. Kilometers a liter. Okay? So it's important that we see how we've configured the equation to be able to cancel out our different units and to be left with the units that we want. Okay? If we don't do that properly, our number, our quantity will be incorrect. Okay? And so a double check of whether our answer is correct is to make sure that we've canceled out properly. Maybe a complex one, a rectangle region, forest measuring 5.6 miles by 9.2 miles was destroyed. Compute the area of this region and can express this in hectares or hectares. Of course, the knowns is square miles, the unknowns is how many hectares, and we would have to look at a unit conversion table which we'll have access to for all of our activities. And then we would find that acres to mile, hectares to acre are these conversions, and so we would plug in our equation here, and being cognizant of square miles to be able to cancel out, right, and acres to be able to cancel out, and putting those in the proper orientation in our fractional form. So then we're left with, of course, 13,000 and change hectares, which is a square unit, right, because we went from square miles to acres to hectares, which is a square unit, a two-dimensional unit. So, wrapping up this, the four-step unit factor method is straightforward, right? And we need to be able to learn how to use it, okay? And really the key to that is understanding how to set up the equation to get the units to cancel out. We need to identify our units correctly. We need to use the right conversion factors. We need to be able to sometimes go through multiple conversions to get to our solution. And we should always look and double check that our units are appropriate based on that they cancel out correctly. Okay, that's a way to back check or to double check your solution. Okay, so now we're going to spend a couple minutes on sig figs. I'm going to go through 5 rules of how we determine sig figs, and then we're going to do a little bit on rounding as part of this. So the first rule, all non-zeros are significant. Okay, so each of these numbers has numbers that are not a zero, so they're all significant. So that's 4 numbers, 4 sig figs. 2 numbers, 2 sig figs. Looking at zeros between non-zeros, so anything that's a zero in between 2 numbers that aren't a zero, we think of that as those are sig figs. Okay, so there's 4 sig figs there. Even though that 0 is there, it's bounded by 2 non-zero numbers, so we're going to count it as a significant figure. If we look at leading zeros, okay, and these are not significant if they're leading on the left. All this is doing is showing us how small of a number that is, or where the decimal place goes. Okay, there's no other reason for those zeros to be there other than to show where the decimal place is. Okay, so those are not significant. So we have 1 sig fig, we have 2 sig figs. Trailing zeros. If we're talking about decimal value numbers, okay, and we take the time to put a trailing 0, you better believe that that's important. Okay, so there's a reason why we put that trailing 0 if it's a decimal. So if you see the decimal value on the left there and you see a trailing 0, that is significant. Okay, that's how we show numbers like 0.5, 0, or 0.250, right? We're showing the precision of that number. Rule number 5, probably the most confusing or most confusing rule. The rule states that when a number ends in 0, that is not to the right of the decimal point. The zeros are not necessarily significant. So this is very hard sometimes to interpret. What does that necessarily mean? So 190, some people would say has 2, has 3 significant figures. This number, some would say 3 or 4 or 5. In this class, to resolve this issue, we will add a decimal point to these types of numbers when performing calculations. So if you have a number that ends in trailing zeros, okay, we're going to put a 0.0 on it. Okay, all this does is it doesn't change the precision, it doesn't change the number, right? It just allows us to have a way to consistently say, okay, if I don't have a 0.0, I'm going to add a 0.0. Right? So if you were having a number like 1 million in your calculation, you don't want that to be one significant figure because that's going to all of a sudden change your answers drastically, right? Because you have so many zeros there, you're going to knock down to one significant figure and you're going to get rid of a whole bunch of numbers. Okay, so in this class, we're going to add this 0.0, and we're not going to add it for 1, okay? And I'll tell you why in a second here. But 1 is usually considered just 1, and a lot of times it gets into our equations from conversion table factors, right? And we'll tell you why in the next slide here. But anything that's 10 or above, right, that has a trailing 0. So greater than or equal to 10, we're going to add that trailing 0. And that's how we're going to determine our sig figs. So in numbers that we use from conversion table numbers, okay, those are considered exact values, and so significant figures do not apply. So any number that you pull from your conversion table, you're not going to use that to determine sig figs. That's basically a free number. If we multiply and divide, we always go with the weakest link, meaning we always go with the answer to the number of sig figs based on the number that was in our equation that had the least amount of sig figs, right? So we have 4 sig figs, 3, and 4, so our answer is going to be 3. We're going with the weakest number of sig figs or the lowest number of sig figs that we use in our equation. That's what we use in our solution. Similarly, when we add or subtract, we just look at the fewest decimal places. Okay, so not sig figs, but the fewest decimal places. So our answer, we only go to that many decimal places. So these are rules that we're going to use for sig figs. They allow us to get more precise, accurate numbers without being overly precise and overly accurate that it really doesn't need to be or waste our time. So we're going to use these sig fig rules. We're going to use these multiplication, addition, subtraction, division rules. We're also going to use rounding. And so probably a lot of us don't have too much trouble with these first three. So the digit being removed, if it's greater than 5, there's no number after it. The number we save or that we round goes up by 1. So a situation like 3.56. Of course, this is above 5, so we round this up to 6. Similarly, this is a 3. We don't do anything to the 5, right? It just stays. So this is like the round up rule. If it's equal to 5 and the number after 5 is greater than 0, we round up, right? So we want to round this away, get rid of that. This number is greater than 0, so we round up by 1. Okay, so those should be fairly familiar to most of us. Now, round up if odd or round if even. This might be different than some of us have dealt with, but these are 2 more rules or ways to actually make our numbers more precise. If the number we're removing is equal to 5, followed by a 0 or a number that's not, nothing rather, we round the remaining number up if it's odd. So what does this look like? We want to get rid of 5. We want to round this 5. Because this is followed by a 0 and it's equal to 5, and this is odd, we round that up. Okay, so round if it's odd. Similar case, if it's even, we're getting rid of the 5. We don't change it because it's already even. So we only round in this scenario if we're going to round up to an even. Okay, we don't round up to an odd. Okay, so the number we start with, if it's odd, we round it. If the number we start with is even, we don't round it. And only round your final answer. Don't round intermediate calculations. Okay, this will make your calculation more accurate if you only round the final answer. Okay, so do all your calculations. Try and keep your all the numbers in there, and only round your final answer. So remember the 5 rules. We can look back at them. Watch your digits during intermediate calculations. Don't round those off. Put your final answer in sig figs and rounded properly. And then also double check your answers. There's always a way to help ourselves not make as many mistakes by just stepping back and looking, does this seem appropriate? Does this seem right? Let me do a quick check if I've done my calculations and rounding properly. Okay, I'll see you in class.